Welcome to CMPT 300, Introduction to Operating Systems. This is the study edition of the course, and I'll briefly introduce you to the different topics you'll be dealing with, but also in general, what is the concept of an operating system, why does it exist, and what does it do. The operating system in general is a very interesting topic because as systems have evolved over the years, um, the operating system has also changed significantly. There have been a lot of different ones. For example, the most popular ones have been Windows and Linux, right, and Apple. But there have also been newer ones such as, I don't know if you people have heard of GOS. That's one that chooses to run a lot of the applications of the internet and only runs the operating system itself on the hardware. So, and Google has come up with more newer things where the browser is sometimes considered to be the operating system, where today most of the applications run, even things like Google Docs, Word documents, Excel can all run within a browser. So does that make the browser an operating system? These are all interesting questions, right? And obviously there are mobile platforms. People have heard of iOS. And as I go through the class, I'll try to kind of give you a hint as to how mobile operating systems differ from cloud operating systems and desktop operating systems. We'll be using Linux in general throughout this class to do all our work on, and we'll be using it as an example of a mainstream OS to study things on. Okay, my name is Arrvindh Shriraman. This course is held on Tuesdays and Thursdays, and the TA for this course is listed on there, Arun Bharadwaj. I joined SFU in Jan of 2011. My primary areas of research in general are software for multi-core processors, energy-aware operating systems and applications in general for smartphones, and energy-smart data-centric systems where for big data applications. I would like to keep this course interactive, and please do ask a lot of questions. And that's one of the reasons I'm putting up these videos up front, so it's easy for you to come prepared to class. And all the assignments that we'll be doing will be directly dealing with the Linux kernel, and we'll be hacking on it and give you an idea. I'll give you a general sense of confidence that you could get into a real operating system and actually make changes and see those changes take artifact on a real system. All the information discussed today and more can always be found on the class website. The class website is listed down there. We also will be using Google Groups to go over questions and to respond to respond with their answers, and we'll be using it as a general discussion board. Feel free to discuss the assignment with these other students, but in general I require all the code be your own. All right, so the topics that we will be covering in this course, the first thing you'll be dealing with is the history, the evolution, philosophy behind an operating system. Like I said, why does it exist? What does it do? What is its purpose? And how does it interact with hardware and user applications? The next thing we'll be talking about is just the user's view of the operating system. What does the user's program perceive? And how does it interact with the operating system? What kind of function calls does it make? Why does it need the operating system? What are the kind of functionalities that the operating system provide that the user application just can't access on its own? Then we'll be looking at tasks and processes, which are the fundamental abstraction of work in operating system. You want to get anything done in your applications or any real work done on your system, then it has to be encapsulated in this notion of a task or a process. So think of it as a vessel that provides an execution model. Then we'll be looking at inter-process communication. So if you want to do anything useful, then applications have to interact with each other, and you want to be able to take advantage of other applications that other people have built. And so we'll be looking at how applications or processes interact, the different kinds of processing interaction models, concurrency, for example, what happens when uh, two applications want to use the same resource at the same time. How do you allocate resources between them? How do you manage their interaction, so on and so forth. Then we'll be looking at scheduling and dispatch, which mainly deals with when you have a lot of different processes and a finite amount of hardware resources, then the question becomes how do you vend these over time? In the sense, their hardware is a contingent resource, it's a limited resource, but there are a lot of different applications that want access to it. And so you want to be able to look at what kind of policies you put in place to vend out jobs or work or time on this hardware to these applications. For example, do you want to be fair and give each application a uniform amount of time, or do you want to give some applications higher priority, like the ones that possibly are interactive? Things like that. Then we'll be looking at one of the most important, the other most important concept in the operating system, which is physical and virtual memory. Memory is essentially any state in your program. So, for example, you have variables, objects, data structures. How are these maintained? How do you vend out main memory so that your application can store data on them? So, if your processes are your execution substrate, then your physical and virtual memory are your state holding substrates, where your application wants to store some amount of data, and the virtual memory and physical memory provide an abstraction to store these. File system and I/O is an extension of the memory abstraction in the sense that they also talk about state, except they talk about persistent state that persists across application invocation. So when your application dies, this is data that's still left behind. So you may want to do this, for example, when you want to output things on the screen, right? So you want to output a file and then read it later on in time. I/O is a more general purpose notion of files, so you can not only have things like files, but you also have things like screen, printers, USB devices, um, character devices, LCD screens. How do you interact with these? So I/O is just an overall general encapsulation of all these different devices you interact with. Finally, as we all know, the operating system also needs to provide security and protection. So this essentially deals with when you have multiple applications running together at the same time, how do you make sure that one does not trample upon the other? How do you make sure that one application's bugs does not affect the other? We already have seen evolution where browsers in the past, if a single tab crashes, brought down the whole browser. But now, if you have only one tab crash, if you have a single tab crashing, then that goes away, but the rest of the tabs still continue to run just fine. This actually makes use of operating system ideas, and so we will be looking at how is that possible? How is it possible that on a system, one part of the system crashes and is able to restart without affecting any of the other parts of the system? So with that, the first question you really want to ask yourself is, what is an operating system? So if you're going to study about operating systems, we got to fundamentally think about what is it? What does it need to do? And what can it be? So in order to understand that, first you got to understand a bit about the overall organization of the system. This may be familiar to a lot of you, but I just want to repeat it so that we get it clear in our heads. A computer essentially is a machine designed to perform some set of operations specified with a set of instructions called a program. This is what you guys write. You compile, you build, and then you run it on the system. And if you look at it, the substrate that actually runs this is the hardware. So you've got keyboards, mouse, screen, CPU, other forms of hardware these days. And these are the components that are actually putting out things, output, or actually running your program. And if you look at the software aspect that you wrote, then it refers to the program that describes the steps we want the computer to perform. But then there's this intermediate step essentially that says, I wrote this program to run on this machine. The machine ran it, but then there's some software piece that ran in between that actually moved my program to the point of running on the hardware. That is, it took my program that I built and then it actually threw it onto the hardware so that it can run it. That piece of software is the operating system. So the operating system is essentially a software that manages the hardware, controls the hardware such that it's shared between many applications, and it also gets the application to the point of essentially just being a set of instructions to a state of being able to actually run on the hardware. So it really has two duties mainly. It manages the hardware and makes sure your applications can run on the hardware. And then when multiple applications want to share this hardware, then it vends out the hardware such that each application gets its fair share of time or some based on some priority with this hardware. And if you look at a computer system, essentially these days you have one or more CPUs, device controllers connected by the bus, and you have all these different devices possibly running at the same time, and they all possibly share memory. For example, your graphics unit and your CPU typically share memory. For your frame buffer, which is essentially the thing that goes on the screen. And one of the interesting tasks of the operating system is to make sure that all of these devices work in concert. That is, when you hit a keystroke on the keyboard, it appears on your screen, and in the middle there's the CPU interacting to figure out what key you actually hit. All of these things the operating system has to control. When the keystroke actually comes in, it doesn't directly go into the CPU. There's some piece of software that's sitting there trying to figure out what keystroke you actually hit. And then it's trying to render on the screen or put an output onto the screen that says, okay, hit this key. All of these processes or applications need to be controlled by the operating system. Its task is particularly made challenging by the fact that we don't have just one type of keyboard. We have 100 different kinds. You have 100 different kinds of printers, different types, like laser versus dot matrix printers, and inkjet printers. You have screens that with varied resolutions. And in some ways, your user program wants to interact with these hardware devices, except that if there's so many different kinds, then you can't be rewriting a program to interact with each piece of hardware. In a sense, why do I care if it's a 1280 by 1920 by 1200 resolution monitor versus a 1280 by 1024? Your application shouldn't have to worry about this. And so, in some ways, one of the main jobs of the operating system is also to provide a universal abstraction to the application itself, to make sure that all monitors appear in the same way to the application, and you shouldn't have to worry about some of the specifics of each monitor. And with that, I want to continue talking about operating system, but I want to take a little bit of a break and actually present technology trends. So one of the key things is that the operating system itself as a piece of software evolves based on what hardware it runs on. So you want to think a little bit about how we've changed hardware over the years. So everyone I hope is familiar with Moore's law. Essentially, it talks about it was an observation made by Gordon Moore, one of the co-founders of Intel, back in 1965, that said that the number of transistors on a chip would double roughly every 18 months. So it was a very simple observation based on manufacturing trends that said we're just going to get twice as many transistors every 2 years. It's worth revisiting this in today's context, because what this has done is over the years people have taken this and translated it to performance, which is a graph you see over here. And oops, give me one second. Okay, so if you look at this graph, this axis is the performance, and this axis is the number of years, and this is the number of transistors. And as we've increased the transistors, we've also increased performance, right, on an exponential curve. And today we increase performance by essentially doubling the number of cores. And this has important artifacts. For example, typically an operating system used to have one CPU scheduler. Now it needs two or more based on how many processors there are. But the application doesn't want to be rewritten for every system out there. In a sense, if you built your application on a system that had only 4 cores, and then you suddenly moved it to a system that had 8 cores, does your application need to change? Is the interesting question. And in general, another thing that we want to think about is the data-centric world that we've now moved into. So today, if you think about what computers do, an operating system need to worry about this because essentially they need to think about what applications they're running. So if you look at it, we have sensor networks. There are all kinds of sensors that are embedded in our world these days. That people monitor traffic. There's a camera at every traffic light. Like you pretty much know everything that's going on the road these days, or someone knows. And you've got things like your cars have gazillion sensors, right? Your cars actually run an operating system within it. I don't know if you guys know about this, but essentially most cars these days run a simple stripped down version of your Windows or CE or whatever, and that pretty much control all the media and even in some cases the engine management unit and things like that. And if you look at databases, things like Facebook, Google, search, this has been going on for a while, and they pretty much collect all kinds of information about us. Right? So they know everything that we do in our lives. And if you think about what kind of operating system can be used to manage this scale of data, then that in its own is an interesting question. People like Google and Facebook do not necessarily run the OS that we all run daily on our lives. They specialize in a lot of different ways to be able to handle this data workloads that they're going to throw on the system. And then you've got things like online games and commerce, which have their own set of challenges. For example, how do you play OpenGL games within a browser? There was a leading company that used to do that. And their systems had to be very latency tolerant because latency was very critical for them. For example, you hit a keystroke, I want the character on the screen to move immediately, and the whole thing began to progress. This is very different than if I check for my email. If I check for my email, then possibly I could slow down certain things. I'm thinking of servicing a lot of people's emails. I'm not necessarily always worried about latency. I can delay things a little bit. But with games, you obviously cannot. Then finally, there's the whole scalable and reliable secure services. So if you think about with most of the data moving online these days, for example, I use Dropbox. How do I know my data is secure? What does the company guarantee me? Is my data all encrypted? What encryption technology does the operating system support? Um, so on and so forth. So the reason I bring this up is that your operating system essentially in a lot of these cases has close interactions with the application themselves. So it's in a lot of the cases it's aware of what application is going to run and optimizes the system based on the specifics of the application itself. So another stat that I want to put up, and this is from David Kahler, who is the famous faculty in Berkeley, the person who invented cluster computing. So he thought about the ratio between the people and the number of computers. And this is interesting in itself because this has impact on who or what agents the operating system is going to be interacting with. So if you look at it, the x-axis is the years, the y-axis is the number of people per computer, and we're looking at how systems have evolved along this axis, right? So if you look at the early years, in the early system, there was possibly, machines were expensive, there's possibly one machine for every 100,000 people, or maybe even more, one machine for every million people, or 100 million people, right? And then as you kept evolving, we went from that to sharing computers between people more effectively, where a lot of scientists had access to computers, to personal computers, where you could do a lot of the tasks, a lot of the daily tasks, such as authoring documents, things like that, on your own personal machines. And then we went into supercomputing, where we had a lot of machines per person. Right? Each person had hundreds of thousands of access to hundreds of thousands of machines, and this brought to a lot of scientific breakthroughs. You can't think of any scientific breakthrough today that didn't come through without supercomputers, because they are the ones that crunch the numbers, and figure out if the principle you proposed is true or valid. Then we have today moved into a more um, streaming information world where there's not much separation between humans and machines. For example, I'm carrying my iPad. I'm actually annotating these things on my iPad. My computer is the one recording the video itself. And I have a phone on me that I'm possibly interacting with as well. So I myself personally at this point, I'm carrying 3 devices. And if you look at all the different devices I'm interacting with, then there's a lot more. For example, this interaction service, the software that I'm running that allows me to interact with this presentation itself is running remotely. And that's running a cluster of machines. So I'm really harnessing the power of a lot of different machines to um, make this presentation itself. So if you think about it, the question is then, what is the job of the operating system? Is the job of the operating system purely now to manage applications on a single system? Or do we also need to take into consideration the fact that what we're really using these machines for is interacting between themselves? So for example, when the iPad interacts with the computer. In such cases, what is the role of the operating system when machines interact? Right? Does it have a different set of rules when machines interact? Does it make things simpler? Does it make things faster? What are the different kinds of machines it can interact with? And how does these interactions change? And so these are all interesting questions that have critical impact on how the operating system evolves. And with that, I'm going to you may take a 30-second break here. We'll actually move into more hardware trends and the different aspects of an operating system in the next video.